magnetism, extreme space weather, and gross electronic infrastructure, including the vulnerability of our power grid to extreme cold solar smoke. This topic was inspired by the latest edition of the IEEE Spectrum. I'm not really familiar with that, but I'm sure
Good.
it tells about it. I've heard of it, but I don't know that much about it. So, that's about all I'm going to give away, as he said. Save the shock effect. Experiment.
Thanks a lot. A little white. Yeah. See the slides. You guys see it all right?
That's good.
Pretty much. All right. Pretty good there. See that? Everybody see that all right?
I've seen that there before. I just don't remember where.
Oh. Yeah. The internet's a wonderful tool. The worst natural disaster in recorded human history hasn't happened yet, but it's a very real possibility. And we're going to talk about a hypothetical scenario. Let's imagine you walk out one night and you look up in the sky and you see flickering lights, yellow, green, violet, and it's a beautiful light display. What you're actually witnessing is the auroras. People start texting, they start tweeting, they start emailing each other about the phenomenon, and it's an awe-inspiring event.
I thought we were
What you guys LSD? Shortly after this, something strange happens. The beautiful colors turn a deep blood red, and panic quickly sets in. Shortly after that, sparks begin to fly all over the country. Transformers blow out, power grids shut down, the electricity goes off. All you hear is the sound of chirping crickets, and it goes dark. The power goes out, and it doesn't come back for days, weeks, months, years. No running water, no food distribution. Panic sets in, violent crime takes over. No medicine is distributed to patients who need it, and within a year, millions of people are dead. And this is a scenario that was outlined in a report by the National Academy of Sciences in 2009. And it talks about the effects of extreme space weather. And it was also featured in this issue of the IEEE Spectrum. I'm an electronics engineer. I graduated from Christian Brothers, and I subscribe to this magazine. So that was the inspiration for today's talk. The author, John Campenman, has been studying this phenomenon for the past 30 years. And the report in the National Academy of Sciences was highlighted in the article that he wrote this past month in the IEEE Spectrum, and that's the inspiration for what I'm going to be talking about today. Now, what causes a storm like this to occur? It's called a coronal mass ejection. A coronal mass ejection, or CME, is literally when the sun lifts off a large portion of super magnetically charged material from the sun's surface, and it comes spewing toward Earth at a very, very high velocity. Now, our Earth's magnetosphere protects us from that, but in extreme cases, it doesn't matter. We can still experience a tremendous impact from the coronal mass ejection. So what is a coronal mass ejection? Imagine the power of 10,000 nuclear weapons coming flying at you. 10 to the 25 joules worth of energy, or 100 million times the most powerful nuclear weapon that mankind has ever devised. It has over 10 billion tons of solar plasma, approximately the mass of the entire Mississippi River, or 100,000 aircraft carriers. More mass than Mount Everest, in the form of superheated, electrically and magnetically charged plasma, flying off the surface of the sun, spewing through space at very, very fast, over 2,000 kilometers per hour, and it interacts with the Earth's magnetic field, and it causes these storms. What happens is it sends ultra-high voltage through power lines, that melts the wires, it explodes the transformers, overwhelms our power system, and there's massive collapse all over the continent. A direct hit is a rare occurrence, but it has happened before. We'll talk about the history of it, and when it does happen, and if it did happen again, given how much our infrastructure has developed over the years, it would be a catastrophic event. Now, to be maximally effective, coronal mass ejections, which come from solar storms, basically have to be launched from the center of the sun so that its trajectory is on a direct line with the Earth. It has to be fast moving. In other words, it's moving over 1,000 kilometers per second, and it has to have a lot of mass. Kinetic energy, 1/2 mv squared. So the more mass it has, the more energy it has. And the faster moving it is, the more energy it has. So, you know, coronal mass ejections happen all the time on the surface of the sun. But during periods of solar maxima, which we're entering right now, through the spring of this year and on into next year, they occur more frequently. And typically they miss us. But what we're seeing is that the power of the solar storm is increasing, and it's only a matter of time before we get hit again. The other thing is the orientation of the coronal mass ejection. The magnetic field, in order for it to be maximally effective and cause a geomagnetic storm, the polarity of the coronal mass ejection has to have an orientation opposite that of Earth. In other words, a southern polarity. And we'll talk more about that, why that is. So let's talk about magnetism. We all know what it is. Quick review. It's one of the 4 fundamental forces of nature. You got the strong nuclear force, the weak nuclear force, gravity, which we all know is not really a force. It's an acceleration caused by the curvature of space-time. But we'll assume we live in a Newtonian world. So, and then you have electricity and magnetism. It's one of the most mysterious forces. We experience it every day. I mean, it's the force that holds atoms together. It's what prevents us from walking through walls and falling through floors. As we all know, our matter is contained of mostly empty space. You know, the dimensions of atomic nuclei are the dimensions of atoms are on the order of angstroms, and the dimensions of atomic nuclei are on the order of femtometers. So an angstrom is 10 to the minus 10 meters, and a femtometer is 10 to the minus 15 meters. So there's 5 orders of magnitude between the dimensions of an atomic nucleus and the first valence shell of an atom. The way I like to think about it is, pick your favorite stadium. You know, Dallas Cowboys Stadium. I'm not a Dallas Cowboys fan, but let's say you were standing at the center of the star in the Dallas Cowboys Stadium, and the perimeter of the stadium represented the first shell of an atom, the first electron shell of an atom. The nucleus of that atom would be the size of a grain of sand. So most matter is contained mainly of empty space, and it's the magnetic attraction or the magnetic repulsion between the protons and the electrons that makes matter solid. So it affects how stars condense, it affects how black holes form, and all solar activity is essentially magnetic activity. So the sun is this big ball of plasma that has moving currents on it, and it has multiple magnetic poles that tend to get intertwined and twisted, and when that happens, then there can be a release of a tremendous amount of energy, and that's what causes a magnetic storm. We have solar flares, sunspots, and then there can be a coronal mass ejection that follows, flings all this material into space. So the Earth's magnetic field is what shields us from these magnetic events. Other than our atmosphere, the Earth's magnetosphere is the single most important entity as far as making sure that life exists on our planet. So you compare Earth to Mars. Mars is probably the most mysterious planet in our solar system. When we look at the surface of Mars, we see evidence of channels that have been carved out, and it's now believed that at some time in the distant past there was actually water on Mars, and the climate of Mars was more Earth-like at one point. But for some reason, Mars's magnetic field died, and the solar wind stripped away the atmosphere, the water evaporated, and the planet died. So the magnetic field of Earth is what shields us and protects us from events like solar magnetism and extreme space weather. So the magnetic field extends about 43,000 miles above the Earth. Its average strength is about 60,000 nanoteslas. It's our shield. The interesting thing is every few 100,000 years it flips polarity. It's not a static, constant thing. The magnetic field is generated by moving currents within the Earth. And it's like a dynamo. I mean, a dynamo is a device that transfers mechanical energy to magnetic energy. And every so often it just flips. North becomes south and south becomes north. And we're actually overdue for a magnetic pole reversal. 780,000 years ago was the last time it happened, and 50,000 years before that it flipped again. So the interesting thing is, if this happens, there may be a period of time when our magnetic field is weakened slightly, making us more vulnerable to attacks from solar events. Now, what is a geomagnetic storm? It usually occurs during a solar maximum. Every 11 years, there's an increased activity of solar spots and solar activity. We're actually entering another period of solar maximum now through the next year. And basically, you have a large solar flare that sends highly energetic particles, and a severe storm occurs when there is a CME shock wave. A lot of mass moving really, really fast toward the Earth. Interacts with the Earth's magnetosphere, and what happens is it actually compresses or collapses the daytime side of the magnetosphere. In fact, it can collapse as much as from 64,000 kilometers down to 25,000 kilometers. And then it swells up the magnetotail, or the dark side, the nighttime side of the magnetosphere. And what happens is part of it will actually break off and fly out into space, and then the other part will snap back like a broken rubber band and eject supercharged plasma back into the Earth's atmosphere and create an extremely large current above the Earth's atmosphere called an electrojet. And this is what actually causes the auroras that we see in the polar regions. So you see a diagram of it here, the solar wind, and it's actually the magnetic phenomenon of reconnection, which is the term that is used to explain what happens after it interacts with the solar wind and ejects the plasma back into the Earth's magnetosphere and causes these events to occur. So what happens after the magnetosphere reconnects and the superheated or the supercharged plasma is forced back into the magnetosphere is a geomagnetically induced current is produced. So the diagram kind of shows it here. You have basically variations of the ionospheric current up here, which through Faraday's law of induction induces an electric field at the surface of the Earth. And that electric field is what drives a geomagnetic current through the ground. All right? Now, our infrastructure becomes an antenna or a conductor of this geomagnetically induced current. So you have high voltage transmission lines, gas and oil pipelines, railways, undersea communications. All these things are good conductors of this geomagnetically induced current that is produced during a solar storm. So the severity and intensity of storms, there's actually several different metrics. And we'll talk about a couple of them that are actually used to measure the intensity and the severity of a storm. One of them is called the Disturbance Storm Time Index, or the DST. And what this measures is the globally averaged change of the horizontal component of Earth's magnetic field at the magnetic equator. And this is computed once per hour in near real time. And during quiet times, when there isn't much activity, it's usually between negative 20 nanoteslas and plus 20 nanoteslas. Now, during a solar storm, it's measured in 3 different levels. So if the minimum of the DST is between negative 50 nanoteslas and negative 100, we have a moderate storm. If it's between -100 and -250, then it's an intense storm. And anything less than -250 nanoteslas, we have a severe geomagnetic storm. The more negative the DST is, that implies that the Earth's magnetic field is actually weaker. More and more charged particles are being infused into the Earth's environment, creating higher currents. So the storm is more intense. So that's basically what DST is a measure of. So the way I think of it is, the more negative the number, the worse the storm. And anything less than -250 means we have a severe storm. The other scale is called the G scale. And it's basically a 1 to 5 scale, 1 being the least severe, 5 being the most severe. And it's based on an 80-year-old parameter called the K index, which has a 0 to 9 scale. And that reflects the change in the Earth's magnetic field over a 3-hour period. So if you have a K index of 9, which corresponds to a G index, a G scale of 5, then you have a magnetic field variation that exceeds 500 nanoteslas. So that's what's meant here. But this is really not that accurate of an indicator as far as measuring the impact of a geomagnetic storm on our existing infrastructure. What scientists like to really look at is the DBDT, which is the changing rate of the magnetic component of the electromagnetic field with respect to time. So it's not just how much it changes, but how quickly it changes too. Because you could have a 500 nanotesla variation in the magnetic field that occurs over several hours, and that would not be nearly as significant as a 500 nanotesla change in the Earth's magnetic field that occurs over, let's say, a few seconds or a few minutes. So DBDT is really the measuring factor when looking at the severity of the storm, and that's measured in nanoteslas per minute. So a lot going on here. We've got DST, we've got G scale, we've got DBDT, but DBDT is really the parameter that's of most concern when measuring the severity and intensity and the impact of a severe geomagnetic storm. So let's talk a little bit of history here. Back in March of '89, 23 years ago, there was a storm that hit the Northeast, and it actually affected Quebec. And 6 million people were left without power for 9 hours. And it actually impacted the eastern United States. In fact, the eastern seaboard dodged a bullet. It could have been a lot worse than it actually was. There was a later surge that destroyed a transformer at the New Jersey nuclear power plant. You can see auroras as far south as Texas. And minimum DST for this storm was -589 nanoteslas. So this is kind of the last time that we had a severe impact from a geomagnetic storm that affected life on Earth. But the worst storm ever, and the one that kind of all future storms are going to be measured by, is the 1859 event. It's otherwise known as the Carrington event. And this is known as a solar superstorm. And it's called the Carrington event because it's named after the guy, Richard Carrington, who was an astronomer at that time, who was observing solar activity on the sun. And he witnessed 2 bright white flares. And this is before there was any understanding of how solar activity impacted activity on Earth. This was 100 years before we understood what the solar wind was, and before we knew what coronal mass ejections were. So Carrington witnessed a bright solar flare on the surface of the sun, and a few days later, there were effects that were witnessed on Earth. There was a massive coronal mass ejection that was released that took 18 hours to get to Earth. Now, normally it takes 3 or 4 days for a CME to get here, so it was extremely fast moving, which means it had a lot of energy. At that time, there was no electronic infrastructure like there is today, but there was the telegraph system. And telegraph operators actually witnessed sparks leaping from their equipment. Some of them were shocked, and some of them, there were even fires that started. And in fact, in some cases, the telegraph operators were actually able to disconnect their telegraph systems and continue to send signals via telegraph by just a connection to ground. That's how powerful the current was. Aurora was seen as far south as Cuba and Hawaii, and gold miners in Colorado woke up in the middle of the night, and the auroras were so bright that they actually thought it was morning, and they started making breakfast. You could read newspaper print in the middle of the night by aurora light alone. It was the largest storm ever recorded, and it had a minimum DST of negative 1,750 nanoteslas. We said earlier that a severe storm was negative 250 or less. So this was a major, major storm. And it occurs once every 500 years, roughly a 500-year event. If a storm like this were to happen today, it would be catastrophic. It would decimate our power grid. We would be left without electricity for years. It would take us at least a decade to recover, and it would cost several $1 trillion worth of damage, and millions of people would die from the outcome. So this is the Carrington event.
Chairman, what would it actually do to the power grid? Just melt transformers, or would it take out all the wires between the terminals, or what would it actually go down?
It would actually be both. It would melt the wires, but the biggest thing, and we're going to talk about that in just a second, is the transformers, the impact that it will have on the transformers. So you can see a comparison here of the three events. Go back to 1989, negative 480 nanotesla per minute DBDT. You know, relatively minor compared to 1921 and the Carrington event in 1859. Both storms were about 10 times worse than the 1989 event. And the real concern is that we could have another event like 1921 or 1959 happen again. So you can see a comparison from the IEEE article here of the footprint of the March 89 event versus the May 1921 event. You can see that the footprint in terms of the impact area from the 21 event was much wider, and the storm was much, much more severe, about 10 times stronger. And the Carrington event was even worse. So getting back to your question, the biggest issue is what are called extra high voltage transformers. As our electronic infrastructure, our electric grid has evolved and developed over the years, more and more of these extra high voltage transformers have been developed and implemented and are now an essential part of our power grid. Now these things here are not easy to build, okay? These are the most likely to fail during a geomagnetic storm. And 345 kilovolt or higher extra high voltage transformers, first of all, they weigh 200 tons each. They cost about $10 million a piece. And to build one requires a minimum of at least 6 months. It requires exquisite craftsmanship and extremely high skilled labor that you don't find. It takes years for somebody to learn the skills to build one of these things. And no global stockpile currently exists for these things. Hit with a 300 ampere geometric GIC, a high voltage transformer's paper tape and insulation will burn, its copper winding will melt, and the transformer will fail either immediately or in the near future. If one of these things go out, it's $10 million. There's about 300 of them in North America. So you can imagine a Carrington level event hitting us and all 300 of these things going out at once. It would be catastrophic. You don't just go on eBay and order one of these things or go to the hardware store.
I guess it would be just, limited to like the area of the United States or something, not all over the world.
It would be all over the world.
Make kerosene go up with it.
Yeah, that's what we're talking about. Yeah, that's a good point. So in the USA, the extra high voltage portion of the power grid has grown by a factor of 10 since 1950. It's even worse in China. The higher the voltage of these transformers, the lower the resistance of the transmission lines, and the more susceptible they are to being hit by a geomagnetically induced current. So China is even worse. The highest of these transformers in terms of voltage in the United States is 765 kilovolts. But in China, they go up to 1,000 kilovolts. So this is a global footprint. A storm like this would impact not only North America, but it have severe impacts in both Asia and in Europe. Higher voltages, and we talked about this, less resistance on the line, more susceptible to GICs flowing. But China is just following a worldwide trend. As utility companies continue to develop, there's a push toward higher voltage transformers so that you can have lower resistance on the line and less loss in terms of signal propagation. But what they're overlooking is how vulnerable our infrastructure is becoming to a severe geomagnetic storm. Manufacturers presently have a backlog of nearly 3 years. This is from the National Academy of Sciences report on this problem from 2009. So this report is 3 years old. Manufacturers presently have a backlog of nearly 3 years for all extra high voltage transformers, 230 kilovolts and above. The earliest delivery time quoted for a new order is early 2011. Of course, again, this is 3 years old. Nothing has changed. If we want to build and develop and implement a new extra high voltage transformer, you're looking at roughly 2 to 3 years just to get one of them out. Only one plant, I'm sorry.
I was just curious, if something like this happened in countries like Australia and up toward the poles, would they be affected as bad?
Oh, absolutely.
They would? It
Oh,
would make any
absolutely.
difference because they're down a little bit?
Probably worse.
Probably worse because they're near where the electrojet, the current is being pushed into the polar regions of the country. So if anything, lower latitude countries are going to be less vulnerable.
They'd be worse off.
They'd be worse off.
Okay.
But it can happen globally because you can have an electrojet not only in the polar regions but also toward the equator. If you get a direct hit from a
I
coronal
was
mass
thinking
ejection.
more like the equator, maybe in the polar latitudes.
Yeah, it would be less severe near the equator than it would be toward the polar.
So I don't think that happens.
Yeah.
Okay.
So only one plant exists in the U.S. capable of manufacturing a transformer up to 345 kilovolts. No manufacturing capability exists in the United States to manufacture a 500 kilovolt or a 765 kilovolt transformer, which represents the highest group of at-risk transformers in the U.S. right now. We have dozens of these things in our power grid, and we can't make them. So if they blow, we're screwed. You can see here from the report areas of probable power loss. You can see the Northeast and the Midwest would be impacted the worst, and then the Pacific Northwest also. Of course, I live in Mississippi, and there's not much going on in Mississippi, so we got nothing to worry about. But this is in the event of a 4,800 nanotesla per minute DBDT geomagnetic storm on the scale of a 1921 or an 1859 Carrington level event. So let's talk about what would happen during a magnetic apocalyptic scenario. Phase 1, you have high energy gamma rays and X-rays from the sun that travel at the speed of light and get here in 8 minutes. And if our satellites in orbit would be vulnerable to being hit by this energy, and they could be knocked out. If those satellites are knocked out, suddenly you have no GPS, no plane navigation, cable television. Every time you go to a gas pump and do a credit card transaction, that's actually a satellite transaction, so that's out. So we're blinded. Each satellite costs roughly $500 million, and there's hundreds of them in orbit. So there's hundreds of billions of dollars in damage right there. Assuming that it's a coronal mass ejection event, the CME would hit Earth 16 to 24 hours later. Why does it take longer for the CME to get to Earth? Because it's mass. At rest, it can't, it's moving at a fraction of the speed of light, roughly 1%, but it takes time to get here. So when the CME hits, it overwhelms the magnetosphere, large GICs flow, blow out the transformers, and the electrical grid goes out everywhere. It's basically a global-wide blackout. The fallout, no running water within a day. You need pumps to pump water. Food distribution stops because you can't have trucking without gas, and you can't pump gas without electricity. Patients needing blood transfusions, insulin, and critical prescription drugs. Don't get them in time, so they die off. Only the strong survive. Normal commerce breaks down and is replaced by black markets and violent crime. 1/2 to 1/3 of the population of the developed world dies within a year or two. There's 300 million people in the United States. 100 to 150 million people are dead. There's 1 billion people in China. 500 million are dead. In Europe, there's what, 750 million people? So roughly 300 to 400 million people are dead. And it costs between $1 and $3 trillion to replace the infrastructure, and it won't be completely replaced for at least a decade. That's a magnetic apocalypse. There's also another event. Last year we saw this in Japan. No power, we got all these nuclear power plants, roughly 400 of them in the world. There's no power, you can't pump water to cool the reactor core or the spent fuel rods. You need, there's only 7 days of backup generator power. And in order to keep these things cool, you need many high voltage transformers, which are no longer functioning. So you start having nuclear meltdowns and Fukushima level events across the globe. You get an idea here of just how severe this problem is and how much we've overlooked this potential problem. I mean, you know, retrofitting our power grid to be prepared for an event like this is not something that anybody's even thinking about. And yet, it's only a matter of time before we see a solar storm that results in something like this. So, all of this can be summed up in a concept known as space weather. We are not isolated here on Earth. We are a participant in the events of the solar system. So, the sun is producing a dynamic, ever-changing atmosphere throughout the solar system. Events on the sun impact events here on Earth. And the problem is it's hard to predict when the next solar storm is going to occur. We're getting better, but we're still way behind. We're about 50 years behind conventional meteorology in terms of predicting storms. X-rays, solar wind, all this stuff can affect communication, navigation satellites, and of course our power grid. 2 years ago we launched the Solar Dynamics Observatory, and it's really producing some phenomenal pictures of the sun. We're able to measure now magnetism, ultraviolet X-rays, even the sun's interior. And we're actually able to see never before seen close-ups of solar flares, magnetic rain, and even tsunamis on the sun. I mean, you know, instead of water tsunamis on Earth, we can see tsunamis of supercharged plasma rippling across the surface of the sun. So we're getting better at understanding space weather, but we're still nowhere near getting to the point where we can predict or understand when the next coronal mass ejection is going to hit. We're essentially playing Russian roulette with the sun. You know, we came real close in Halloween of 2003. A very, very powerful CME was ejected from the sun that was close to a Carrington level event, but it missed us. So it's only a matter of time before we get another direct hit. I'll wrap up by talking about some preventive measures. 3-phase power lines. I'm an electrical engineer, so I've got to talk a little bit about this. So we basically have 3 phases, you know, each separated by a third of a cycle. And it's a very simple setup. You have a neutral to ground connection right here in the event that there's a high voltage event on this line. And it's assumed that this thing right here is an infinite sink to ground. But in retrospect, this is actually a design flaw, because during a GIC event, this becomes a source of current, which flows through the earth, through the ground, and into the network, melts it out and blows it out. So the solution to the problem is right here. Being able to retrofit the grid to prevent the flow of these DC currents. Now, one solution to this problem is to install what are called low ohmic resistors between the neutral to ground connection that will prevent the flow of GICs into the grid. And implementing this is actually a fairly low-cost solution compared to the alternative, and it would reduce the flow of GICs for storms of all sizes by about 60 to 70%. But this is really only a first level of defense. So it's not a comprehensive solution. A better solution, okay, this is a diagram of what I'm talking about here. So you see the three-phase power network, the three-phase transmission line network here with the resistor in place. And it's a good solution, but it's not a comprehensive solution. It wouldn't totally block all the GIC flow into the network. A better solution is to use capacitors. Capacitors would completely block, the idea is to completely block the flow of current into the network. And it's kind of interesting because you need to have a bypass system in place in the event that on the network there is a fault that occurs and you need to have a sink to ground. So you need a high switching element to be able to not allow the network to function as intended, where the current can flow to ground, but also block the flow of GICs into the network. So there's a company in New York called Advanced Fusion Systems that's developed a device using a vacuum tube. I thought vacuum tubes were obsolete, but now they're coming back and they're going to save the world. It uses a vacuum tube to install this fast bypass of induced currents within a fraction of an AC cycle. And the reason vacuum tubes is because they provide faster switching capability than a mechanical switch, a power transistor, or a spark gap. So the network can function as intended and also have a blockage for geomagnetically induced currents and a fast switching element in the event that there's a fault on the AC network. And a schematic of it is here. So you have the NCBD device, the neutral capacitor bypass device. Here's the three-phase network. And then from the neutral to ground connection, you basically have this network here. Here's your capacitor. The neutral capacitor portion of the device blocks the DC flow from the geomagnetically induced currents, prevent it from melting this device here. And then here is your vacuum tube device right here. And a good device to use for this would be the 4275 Bitron tube produced by Advanced Fusion Systems right here. And that goes right there. So in the event that there is a fault in the network right here, the AC bypass portion of the device provides a momentary path to ground for large AC fault currents. So this fast switching element right here would sink the current to ground and then immediately go back into an open circuit connection and block the flow of geomagnetically induced currents during a potential extreme solar event.
Did you say what the time cycle on that actually was?
I didn't. It's fractions of a second, but I have to look at the literature.
So I remember reading a long time ago about the old Marconi coherers that would protect power lines when a lightning strike occurred nearby. The metallic clumps would coalesce and let the current go to the ground, and then almost immediately go back to
the
where you just see a tiny little flicker, and that would be all there was to it. And I'm not sure what the cycle time on that is, but you're saying this is, you mentioned spark gaps, which I guess is kind of like that.
Yeah.
But
Yeah, this vacuum tube element is actually faster than any other mechanical device that we have, including power transistors or spark gaps. Do you know what the cycle time was for that device?
no, I hadn't read that since grade school, but when I started making things like that to communicate with sparks and things, but I never did measure the times on it.
Yeah.
What is the size? What would this thing? I mean, this is not something that you can bring home. I mean, it's probably huge, right?
Yeah, this is a schematic diagram of it. I have an actual picture from the literature. I didn't put it in the presentation, but yeah, it's not something that you put in your pocket.
If you get out of your old telco radio.
Right.
Radio shack.
Yeah, radio shack.
Do these huge transformers have disconnect switches on them?
Do they? Yes.
So if everything works real quick in our satellite, say it detected one of these flares coming out 8 minutes before it got here, could it be potentially leaking?
Yes. In fact, it's another preventive measure.
It'd be days, actually, because you could get the electromagnetic radiation first, and then The actual mass ejection wouldn't be here for another couple of days. You'd have a chance to disconnect everything, which would be an inconvenience, but not as bad as having it permanently ruined.
Yeah, that would be the solution right now, since this has not been implemented yet. Have the SDO look at the sun, see the solar flare, like you said, 8 minutes later, we know it's, the storm has hit. Let's shut everything down. We have local blackouts everywhere. And then wait until the CME passes and then put everything back online. So, but are we going to do that? I mean, how are we going to be able to predict when the next one's going to hit? We're still, space weather meteorology is where we were in the early 1950s. We still got a ways to go. So the best long-term solution is still retrofitting the grid. So you can see here the operation during a solar event. Where this device right here is preventing the flow. I'm not going to like this in here. Anyway. Okay, so conclusions. We're entering another solar maximum, which means in the next year we're more susceptible and more vulnerable to increased solar activity, including the potential for a Carrington level event. The current infrastructure is dangerously vulnerable to severe solar storms. There's a lot of literature online that's been written, especially by the author of this IEEE article, John Campingman, about this problem. A lot of stuff out on the internet about this. Very few people know about it. It's not something you discuss in layman's terms, but in the scientific community, it's a realistic problem. Space weather forecast is still years behind, but we do have the technology and the solution to actually retrofit the existing power grid. The problem is, our country's broke, politicians are stupid and slow, and do you think this takes priority over other things like getting reelected, or bridges, dams, or whatever? No. So, it could happen tomorrow, it could be several hundred years down the road, but essentially, we're exposed. So I hope you guys all sleep better tonight, knowing that our power grid will go out tomorrow.
That sleeps good in there.
Any other questions?
I was just thinking, if the electricity goes off and we have to make another one of these transformers, there isn't any electricity to make it in the first place.
Exactly. The statistics I showed were assuming that you're operating at optimal or full production. So how are you going to build these things when you don't have, it's kind of the chicken egg argument.
Where do the transformers that we have now come from, since you said we don't have the capability of making any of them? Did we used to have the capability and lost it?
A lot of them come from overseas, Philippines, places in Asia. We have a few places, I think, on the West Coast that can still manufacture them.
The small ones.
Yeah, the smaller one. For every extra high voltage transformer, there's about 1,000 smaller transformers. But what you're asking is the extra high voltage transformers. I think from what I was reading, it's the Philippines and some places in Asia that make these things. And then there's like 1 or 2 plants on the west coast of the United States that's capable of producing them.
They're made in Iran, though,
Not Iran. Fortunately
right? They'll
not.
be there after a while.
Yeah, exactly.
So this could be considered a mass extinction event.
Yeah, certainly could be a game changer for life on Earth. I mean, when you think about how dependent we are on electricity today versus 70 or 80 years ago. I mean, when the Carrington level event occurred in 1859, it was still 20 years before Thomas Edison. So life goes on. But today, I mean, everybody has a pocket computer. And, I mean, just think about all the ways that we're dependent upon electricity and power. Air conditioning and heating, your refrigeration goes out, food is going to start rotting. I mean, our society will literally unravel and unwind. And that's the difference between the way we live today versus the way we lived 80 or 90 years ago when the last superstorm hit. So this is a real problem. This is a real problem. It's been researched, it's been written about. Very few people understand it. But we don't want to wait too long before we act. I mean, I think to me personally, it's a testament to how stupid and how ignorant the human race is, and the fact that it's a miracle that we're still here. I mean, we create this elaborate infrastructure to make our lives simpler and easier, and yet there's a design flaw, a fundamental flaw, and it's correctable. I mean, it doesn't cost that much. It's correctable. But we're, typical human nature, procrastinating, putting it off, and just we're putting ourselves in more of a reactionary state rather than a proactive state as far as addressing the problem.
It's not that we're long ago, because I grew up in the fifties, we didn't have this.
That's true.
We're not that long ago.
Think about when you guys were young. I mean, I was born in '74. In '72, there was a CME event that was faster moving than the Carrington event, but it was not in direct line with Earth. So, the sun is a very powerful entity, and it shoots out these things quite frequently. And it doesn't have to be during a solar maximum. I mean, we can see CME events during a solar minimum also. They're more probable during a solar maximum. But the sun can hit us anytime.
How close to on axis does it have to be kind of as a direct hit? I mean, you could calculate the spherical trigonometry of the thing and just see how many events per century you would expect in a narrow enough cone angle to wipe us out. I'm sure it wouldn't be an absolutely 0 degree head on, but.
No, that's an interesting question. It has to come near the center of the sun, but it doesn't have to be a direct hit necessarily. It could be a glancing blow. And if it's powerful enough, it has enough mass and enough kinetic energy, it can still do a lot of damage.
And the fact that the magnetosphere act as a bad thing and catch something that's kind of glancing and focus it on into us.
Absolutely. If the polarity of the CME is oriented correctly and it hits us at the right time, absolutely. It could grab that plasma and force it right back into the Earth. So yeah, it does not have to be a direct blow.
So the astronauts in the space station are literally toast. Right?
That's an interesting point because
Those are the admins of
when we're talking about astronauts in space orbiting the Earth, or let's say we ever get to the point where we send an expedition to Mars, this solar activity is a major concern. In fact, astronauts in space, I think they have a safe room that they have to go in where they're shielded. And people on Earth, mission control, they have to keep an eye on the sun. And if they see a flare or an extreme solar event, they have to contact the astronauts and say, get into your safe room. Same thing is true with missions to Mars. Let's say we were successful at landing people on the surface of Mars. Well, just because you're on Mars and you're millions of miles away, you would still have to keep in touch with Earth. Or somebody in your Mars mission would have to keep an eye on the sun because Mars doesn't have a magnetic field. And the astronauts would be vulnerable to the solar wind. So it's a concern. In fact, if you had a Mars rover, one of the things you would do is you would outline the rover itself with food packs that would kind of shield you from the radiation. Food packs and urine packs. You store your urine. And you would outline your spacecraft or your rover with that, and that would shield your vehicle from the solar wind. So we get, we take the magnetosphere for granted. We take a lot for granted living on Earth. But you don't have to go very far up before you're suddenly exposed and vulnerable.
Like 50 miles or so?
50 miles, yeah, that's about right. So, anyway, guys, I hope this has enlightened you, and you guys sleep well tonight.
Thanks a lot.
Yes, we will.
That's a good talk, but don't need to spread it.
Well,